Hi, my name is Sergey Levine, and today I'm going to talk about reinforcement learning with large datasets, a path to resourceful autonomous agents. Imagine we want to build a robot that's going to go and explore a new planet. It's going to be out of touch with humanity, so it has to navigate around this planet on its own. It has to make its own decisions. But besides just being able to carry out its initial mission, it has to also react intelligently when unexpected issues come up. It has to be resourceful and flexible. So it's not enough for us to just pre-program a single strategy into this robot. We need to equip it with the tools needed to adapt and learn in the environment where it'll be situated, far from any help. Much like a person who is stranded on a desert island might need to fend for themselves, build shelter, and gather food, this robot will need to use all of its resourcefulness to get by. I want to frame what I'm going to talk about next in the context of this example. Let's think about how current innovations in AI might help bring us closer to being able to build an autonomous agent of this sort. So what are some of the big advances in AI that many of you might be familiar with that we can draw on? Well, there are really kind of two big things that in the past decade have garnered a lot of attention. The success of data-driven AI, most recently exemplified by the rise in powerful generative models for things like image generation and language modeling, and reinforcement learning, where we've seen tremendous successes in terms of the ability to discover solutions to complex strategic problems like playing the game of Go. So let's talk about these two advances and discuss their benefits and their limitations if we want to enable our space exploration robot. So what does data-driven AI do fundamentally? Well, many of you have probably seen pictures and examples that we can get, for example, generative models that are trained on large amounts of images from the web to generate pictures on demand from a textual description. We can get chatbots that will explain jokes, and we can get language models that will solve all sorts of complex problems. We can even use generative models for things like designing proteins and solving problems in the sciences. The fundamental ideas behind all of these approaches are very similar. They're based around density estimation. We take a large data set from the web, and then we estimate either the distribution of inputs in the data set or a conditional distribution P of y given x. So that might be, for example, modeling the distribution over natural language sentences, or modeling the conditional distribution over images conditioned on a prompt. So it's very much like a massively scaled up version of the kind of density estimation that we learned about in introductory statistics. But if we're going to take this perspective, we should of course ask, well, if we're doing density estimation, then it must really matter what our data set is. Like what we're actually learning is, for example, if we use pictures from the web, what kind of photographs do people take, or what kind of drawings do they put up? If we're learning from text on the web, we're really asking what kind of text do people type, right? These are very reasonable things to do if what you want to do is emulate the behavior of humans. And of course, that's exactly what data-driven AI is best at. It provides images, text, and other content that appear very human-like, and that makes it very compelling to us. By contrast, what does reinforcement learning do? Reinforcement learning solves actually a very different problem. Reinforcement learning is about iteratively improving classically through interaction, where you have an agent that interacts with the world, uses a little bit of interaction to improve its policy, then interacts with the world some more, and does this many, many times. And we've seen reinforcement learning be very successful for learning to play video games, solving various robotics tasks, and of course, perhaps most famously, beating the world champion at the game of Go. Now, these things are also very impressive, but for a very different reason. The kind of crowning achievement in the last 10 years, arguably, of reinforcement learning was the kind of emergent behavior that allowed AlphaGo to beat Lee Sedol. And perhaps one of the most notable moments in the championship match was the so-called move 37, where reinforcement learning discovered a move that surprised everyone, even the expert analysts who were very familiar with the game of Go that were watching the game. So reinforcement learning was impressive precisely because it produced the kinds of behaviors that would not have occurred to humans necessarily. In contrast to the data-driven AI systems that are impressive because they produce things that look very much like what people might draw. So here we see the contrast. Data-driven AI can produce very impressive results because those results appear to be something humans might do. And that makes a lot of sense because they're trained to emulate data produced by humans. In contrast, reinforcement learning can come up with novel solutions to difficult problems that are impressive precisely because no person had thought of it. So these are two very, very different capabilities. Now, of course, reinforcement learning by itself doesn't do many things. The examples on the left perhaps notably look very synthetic in contrast to the real world, which has very complex physics, lots of diverse objects, wide variety of environments the agent might find itself in, multi-agent interactions, And there's an enormous gulf between the problems that reinforcement learning solves effectively and real-world problems. It's not necessarily a gulf of strategic complexity, but rather a gulf of breadth and generalization, which I should note are precisely the things that data-driven AI does very well. So if we want to apply reinforcement learning to more real-world settings, if we want, for example, ImageNet level or internet scale generalization, then every time we go around this reinforcement learning loop, we might need to update our model on internet size amounts of data recollected each time we train, and that might get simply impractical. So data-driven AI is great because it's about learning about the real world from data, but it doesn't try to do better than the data. It's really about trying to match the behavior of humans, not discover new solutions. Reinforcement learning optimizes a goal with emergent behavior like Move 37, but it doesn't make use of real-world data, which leaves it with a limited ability to generalize to a wide variety of novel real-world situations. And that's perhaps why some of the biggest successes of reinforcement learning have been in game-like environments, which can be simulated exhaustively without worrying very much about broad generalization. So data-driven AI is all about using data. Reinforcement learning is all about optimization, optimizing the best possible move, the best possible decision, and perhaps leading to emergent behavior. Data without optimization doesn't allow us to solve new problems in new ways, and that's why the big successes of data-driven AI seem to be all about reproducing the behavior of humans. Optimization without data is hard to apply to the real world outside of simulators. So if we want the kind of resourceful agents that can flexibly adapt to complex real-world situations, like our Space Explorer robot, then we'll really need to get the best of both worlds. So can we learn to make decisions and use data? Well, to go there, we'll need to get away from the kind of classical paradigm of online reinforcement learning, where an agent interacts with the world, collects a little bit of data, updates its policy, throws out that data, and then interacts with the world some more, and towards something that looks more data-driven, perhaps much like language models or generative models use large data sets mined from the web. We could use reinforcement learning on large data sets from previous interactions that an agent might have had, or even previous data sets from the web, acquire the best policy we can, and then potentially deploy that policy for some additional online fine-tuning. That way, perhaps we get the broad generalization that we want, but still retain the ability to get those highly capable emergent behaviors like Move 37. So a notional recipe you could imagine for our Space Explorer robot might be that we'll start with a data set of experience, maybe experience the robot itself has here on Earth, or experience that it gets from humans, or maybe even from other domains that are not directly relevant seemingly to space exploration, but might give it some good understanding of intuitive physics and things like that. And that'll be used for offline training. Basically figure out, just like an astronaut would prepare for a journey to another planet, prepare our robot with all the knowledge we have on hand so that it has the best possible initialization. And then off it goes to another planet where it will perform online learning and improvement. That'll give it that flexibility and adaptiveness so that when some novel situation presents itself, it'll be able to combine its prior knowledge with its ability to adapt online to discover a novel solution to a novel situation. Now, to get there, of course, we'll need to develop algorithms, such as algorithms for using offline data to train, and we'll need to develop prototypes that can allow us to study how reinforcement learning, combined with large and diverse amounts of data, can enable decision-making and optimization in combination with a broad generalization that we've seen from the world of data-driven AI. So in this talk, I'm going to talk about what we can accomplish if we combine data and optimization. By optimization, I mean reinforcement learning, optimal control, things that perform some sort of computation to make more optimal decisions. And by data, I mean prior experience. I'll talk about some fundamentals of offline RL algorithms. Then I'll talk about how these ideas can be applied to enable offline RL pre-training in robotics and what that can do beyond the classic online RL paradigms. Then I'll talk about scaling up this idea further to enable training robotic foundation models on offline data that can enable highly generalizable behaviors in the context of decision making. And then I'll bring things back full circle, and I'll talk about how, besides applying the ideas of data-driven learning to RL and robotics, perhaps we can apply the ideas of RL back to generative models trained on internet-scale data to give them new capabilities, to give them the kind of emergent capabilities we might ordinarily associate with RL systems. But let's start with some RL fundamentals. So first, a big question. What is it that we expect offline RL algorithms in particular to actually do? Well, one bit of intuition, which I think is not very good, but might get us started, is that it's a little bit like imitation learning. So imitation learning is probably the best known form of offline learning for decision making. Let's say that you want to go from green to orange. In imitation learning, you would assume that you have trajectories that more or less perform the task, perhaps with a little bit of variability, and your goal is to learn a policy that captures the behavior in those trajectories. Now, it can be provably shown that imitation learning can actually be done better with offline reinforcement learning methods than with direct supervised learning under some structural assumptions, but I think that's not really its main benefit. A better intuition, perhaps, is that offline RL is about getting order out of chaos. Maybe your data doesn't look like good trajectories that succeed at the task. Maybe you want emergent behavior and your data is not so good. Maybe your data goes all over the place and you want to discover how to go from green to orange. Well, offline RL intuitively can combine bits of knowledge that you've seen in other trajectories that might not perform the task you want and figure out how to put them together, how to stitch them together, if you will, to solve some new task. And perhaps there's a very simple and obvious example of this. If you've seen trajectories that go from A to B and trajectories that go from B to C, offline RL ought to be able to figure out how to go from A to C. But that's simply the simplest example. Perhaps a more realistic example is that you have a variety of behaviors that are all highly suboptimal. Maybe these are humans driving vehicles where every human is good at some things. Maybe one person is good at merging on the highway, another person is good at navigating stop signs, but no one person is good in all situations. And maybe offline RL can put together the best bits of each one of them to get a single policy that is better than any one human, that is better than any one example by itself, putting together the best pieces of both in a dynamic way. So if we have good offline RL methods, we could perhaps take this idea much further to get near optimal policies from highly suboptimal data, and that's precisely that kind of emergent behavior that I motivated at the beginning of this talk. So if we want to get into the technical details, I'll give you a quick technical primer to some offline RL methods. This is not really necessary to understand the rest of this talk, but I did want to make an attempt to at least cover some technical material here. So in RL, we have an agent that interacts with the world and selects actions, which we refer to as A, and the world responds with states S and rewards R. And typically, our final aim is to learn a policy, pi of A given S, that selects good actions in each state. How good a policy is defined by the RL objective, which is the total reward the policy will get from selecting actions over the entire horizon of the task. So you don't just want the best reward now, you want the best reward over all time. A very useful object for this is something called the Q function. The Q function is defined as the cumulative return you'll get if you take action A in state S and then follow the policy pi after that. If you can learn a Q function for a particular policy pi, you can recover a new policy that is at least as good or better by taking an action with probability 1 if it's the argmax of the Q function. This is the basis of policy iteration, and it can be extended into a Q-learning algorithm simply by short-circuiting this, by substituting in this argmax into a recursive equation for the Q function. And that's called the Bellman optimality equation. So long story short, if you can learn a Q function that satisfies this equation such that Q star SA is equal to the current reward plus the max over the next Q, if you can learn such a function Q star, then its greedy policy, its argmax policy, will be the optimal policy. So this immediately suggests a way to do RL, which is to learn a function by enforcing this equation at all states. For example, by subtracting the right-hand side from the left-hand side and minimizing the squared difference over a large sample of state action pairs. Now, a very interesting thing about this minimization is that this doesn't actually assume that the states and actions SI, AI actually came from any particular policy. So Q-learning is what we call an off-policy algorithm. Typically, this is used so that as you're running RL, you can recycle data seen in previous time steps through the minimization. But it's very tempting to imagine that Q-learning can also serve as the foundation for a fully offline reinforcement learning algorithm. And that's what we're going to try to explore. So let's just see if we can naively take this Q-learning foundation and run it on entirely offline data, on entirely previous collected data. What's going to happen? Well, it turns out that by itself, this is a very bad idea. And the problem really comes down to distributional shift. And it's distributional shift between the policy that collected the data and the new policy that you're learning, which is hopefully better. To make it apparent how this gets us into trouble, let's take this Bellman optimality equation and rewrite it a little bit. Instead of writing it as a max, I'll write it as an expected value under some distribution pi nu, where pi nu is that greedy policy. It assigns a probability of 1 to the action that maximizes the Q function and 0 to all other actions. Now, I didn't actually change anything because evaluating a function at the argmax is the same as the max. This is exactly the same equation, but it makes it a little bit more apparent that in order for these things to work well, the expected value of Q under pi nu needs to be accurate. So let's refer to the right-hand side as y. If you ever want to know whether the expected value of a function under some distribution is accurate, of course, the first question to ask is what distribution is it trained under? Because if you evaluate under the same distribution that you train under, then you expect your error to be low. So what's the training objective? Well, it's to minimize the error between the left-hand side and right-hand side in expectation under the data distribution pi beta. We use pi beta to denote behavior policy. That's whatever policy collected the offline data set. We don't necessarily even know what this policy is, but we have samples from it, which we can use to estimate this expectation for our training objective. That's how we do Q-learning. But now, of course, you'll notice that you should only expect good accuracy if pi beta is equal to pi nu, which means that the policy that collected the data is equal to the optimal policy that you're learning. How often does that happen? The whole point is to learn a better policy than the one you saw in your data set, which means in general pi nu will not be the same as pi beta, which means that you can't expect these expected values to be accurate. But even worse, pi nu is selected to maximize the Q values. And that's really bad because if you optimize the inputs into a neural net to get a particular output, you can very often fool the neural net to produce whatever answer you want. That's the foundation of adversarial examples. In the same way that adversarial examples can fool an image classifier into mislabeling an image, this optimization over pi nu can fool the Q function into assigning a high value to an action that is not actually good. And that's actually exactly what we see in practice. This is an experiment that we did quite a while back, about 4 years ago at this point, where we naively tried to use Q-learning style algorithms on offline data with different amounts of data ranging from 1,000 to 1 million transitions. And we saw that the policies all behaved pretty poorly. They had a reward of minus 250. But when we investigated the Q function to see what it estimates, here the y-axis is a log scale, the Q function thought it would get a return between 10 to the 7th power and 10 to the 20th power. So it's massively overestimating, and that of course reflects exactly this adversarial examples problem. So long story short, if we want offline RL to work on the basis of these Q-learning methods, then we need to somehow address the fact that we have this distributional shift and we're evaluating the Q function under a different policy than the one that it's trained under, and even worse, a policy that might try to fool it into producing a large value. There are a number of ways to solve this problem, but one particularly reliable approach that we found, that I'm going to use in some of the robotics work I'll present later, is called conservative Q-learning. The idea in conservative Q-learning is to address this overestimation issue in a fairly direct way. If the overestimation resembles adversarial examples, we'll use a method somewhat similar to adversarial training to repair it. So imagine this green curve is the true function you're trying to fit. These are the labels. And the blue curve is your fit. The fit is good in most places, but if you maximize it, you'll find exactly this point where it overestimates the most in the positive direction. So even a very good fit can be exploited. What we're going to try to do is discover these overestimation points and explicitly repair them. So in conservative Q-learning, we have the usual Q-learning objective on the second line. That's basically minimizing the difference between the left-hand side and right-hand side of that Bellman equation. But then we additionally have this regularizer, which aims to minimize the Q values at actions where the Q values are high. Notice that mu is maximized, meaning that we're trying to find a mu such that the actions have a high Q value, and Q is minimized, so we're trying to minimize the value of Q at those points. This is quite similar to adversarial training in spirit, and actually has very appealing theoretical properties. We can actually show that if we use this appropriately with a suitably chosen regularization parameter alpha, we're actually guaranteed to fix the overestimation problem. Now, there are a number of additional design details that are necessary to implement this algorithm successfully, but this is the basic high-level idea. I'll briefly summarize a particular application that we've explored for this method, where we've studied how conservative Q-learning can enable offline pre-training and even online fine-tuning with Atari games. So in this experiment, we trained with CQL to train a single model on 40 different Atari games. So each game had a separate head, and they shared a single ResNet backbone. We had suboptimal data from all the 40 games, and the model was trained entirely with this CQL offline RL method. Now, on the training games, the method performed very well. The improvement over data was, of course, particularly notable when the data itself was suboptimal. That's the left side plot. So the pink bar here is the full conservative Q-learning method with the larger model. The red one uses a smaller, much smaller model. And you can see that with the large model and conservative Q-learning, it significantly improves over the suboptimal data. It even slightly improves over near optimal data. And on the suboptimal data, it's also significantly better than baselines like multi-game decision transformer, which do not attempt to perform offline RL. But perhaps more interestingly, if we train with CQL, it's labeled as scaled QL here, which is the large ResNet version of CQL. you can fine-tune with a little bit of data for an entirely new game that was not seen in training and actually get very good results. So here you can see that across all these games, the pink bar generally gets the highest return. Other methods work sometimes, but CQL with these large models tends to work most consistently. And perhaps even more exciting, you can actually use it as an initialization for online RL. So here we have variants of the games seen in training. So these are new variants, like ones where, for example, there are new levels of the game or new configurations of the board. And starting from the large ResNet trained with CQL, that's the pink bar, the online RL tends to get significantly better results than various other alternatives like representational learning with MAE. Offline RL and conservative Q-learning have been used in a number of settings. I'll talk about some of them in this talk, like robotics. Some that I won't cover, like dialogue systems. Offline RL has been very successfully used in a variety of settings to train dialogue systems to optimize rewards. Of course, Atari games. Other folks have used it for things like e-commerce, optimizing notification click-through rates, so that the algorithm pushes notifications to your phone that you're more likely to actually use. All these things are settings where it's very natural to get lots of data, but comparatively difficult to have extensive online interaction. And offline RL with conservative Q-learning tends to work pretty well in those settings. So those are the algorithm fundamentals, but let me talk a little bit about now how we can take these ideas and actually bring them into interactive real-world domains where generalization and diversity are really important. And I'll start with a discussion of offline RL in robotic manipulation. So can we apply this principle to pre-trained robots? Well, first, if we're going to do offline reinforcement learning, we need a data set. And in robotics, it's very natural for that data set to come from other interactions, other tasks. So perhaps if we want the maximally scalable recipe, we'd like to take all the data from everything that robots have done before, whatever tasks they might have solved, and use that to initialize a very general model that can then be used to provide a degree of generalization when we're learning a new task, perhaps in a more narrow setting. So where do we get pre-training data? Well, later on, I'll talk about how we can leverage data from the web, but perhaps most directly, we can simply collect large amounts of robot data. And that's something that we did recently in what we call the bridge data set. We call it the bridge data set because it's meant to bridge the generalization gap between many diverse prior tasks and a more narrow new task. We recently released the second version of the bridge data, which aims to enable this kind of large set of tasks for new downstream applications. And the dataset is collected in a wide variety of environments with a low-cost WidowX robot. So there are a total of 54,000 demonstration trajectories in this dataset, hundreds of objects, full language annotations for each task. So for folks that want to study language-conditioned policy learning, every trajectory is annotated with a language description, 24 different environments. Many of these environments are these kind of toy kitchen environments that other researchers can also purchase and place in their own lab. The robot is also a low-cost robot. It costs about $3,000 US. So this is a very large data set with a wide range of different interactions that's meant to really serve to provide this foundation of pre-training for a variety of downstream tasks. And we've actually confirmed that policies trained on this data set can be successfully run in other labs. So our colleagues at Stanford were able to reproduce some of our results on their own setup. Here are some examples of policies trained on the bridge data set. First, here's a set of goal condition policies. This is using, in the evaluation, we have a variety of policies, including diffusion models, transformers, and ResNets. These, I believe, are showing the results from the diffusion policies. And you can see that the tasks have quite a lot of variability, including things like pick and place tasks, but also more sophisticated tasks like sweeping objects and manipulating cloth and opening drawers. And here are some examples of language conditioned behaviors. So these are policies that are trained to take in language strings and perform whatever the user is asking in language. So let's talk about the use of bridge data with offline RL pre-training. This work actually uses an earlier generation of the dataset, but similar principles. So here we run a version of CQL in a multitask setting. We call this system PTR, or pre-training for robots. So a very simple way to apply it is to make every task essentially a separate task indicator. We could do this with language as well, but in our prototype, we just used task indicators, meaning there's a one-hot vector that's passed into the policy that indicates which task the robot should be attempting. The earlier version of the bridge dataset, which had only 12,000 demos, was actually used to pre-train this. And then we take 10 trials for some downstream task, and we fine-tune with those trials to actually obtain a policy for the target task. So the idea is not necessarily just to get this multitask policy, but to actually rapidly fine-tune to a new task from just 10 trials. So this can enable us to learn an entirely new skill. Now the skill of course is structurally similar, but it's in a new environment and with a new object. And we can examine the performance of PTR on some of these new skills in comparison with other ways of using the same offline data. A particularly interesting comparison to note here is the one on the right-hand side, where we compare with R3M and MAE. So R3M and MAE are representation learning methods from computer vision that also use the same data, but they're mainly aiming to learn visual representations. And you can see that by comparison, the PTR method achieves significantly higher success rates. So pretraining with offline RL on that prior data, actually optimizing for good decisions, leads to a better initialization for the same kind of downstream online fine-tuning. We also see that the larger the network that is pre-trained with PTR is, the more performant the downstream fine-tuning is. So in this graph, the x-axis is the size of the model, ResNet 18, ResNet 34, ResNet 50, and the y-axis is the success rate on the downstream task. And you can see that larger models achieve higher success rates on downstream tasks. We've recently expanded PTR to also handle an even more diverse source of prior data, which is videos from the internet, in this case using the Ego4D dataset. We can modify the PTR training process so that we can actually train on video data with an RL objective, essentially learning a value function on video data, then fine-tuning that value function further with multitask robot data, and then finally fine-tuning it to a single downstream robot task. We evaluated the system in environments with more distractor objects that present a greater generalization challenge. The V-PTR shown on the left side achieves the highest success rate on these tasks. And perhaps an interesting note here is this comparison. This is the same method, but actually skipping the multitask robot data. So it goes straight from video data to downstream fine-tuning to a single robot task with on the order of 10 trials. And while this is significantly worse than the full V-PTR method, you can see this is actually one of the most competitive baselines compared to other representational learning approaches, which again suggests that representational learning with reinforcement learning methods, in this case learning a value function from video data, provides a better initialization for downstream control. And that's consistent with the hypothesis that I used to motivate this talk, that if we can train with optimization in the loop, with decision-making in the loop, then we'll get better models that are more suited for downstream control problems. Now, what if we can take these ideas further? What if we can scale up models trained for control, not just a variety of environments for a single robot, but maybe even multiple different robots? So can control plus data enable robotic foundation models that can generalize broadly across platforms and even across different problem settings? We started investigating this over a year ago with the Generalized Navigation Model, or GNM. Here we put together robotic navigation data from 6 different robots, 8 different data sets, about 60 hours. And we trained actually a fairly generic model on this data, which is a goal condition policy. So this policy takes in the current observation and an image of a goal, as well as a little context that provides it with a window of recent time steps that it can use to infer what kind of robot it's controlling. Now, besides this, there are actually no specific technical modifications to accommodate the multi-platform setting. The model is simply trained on all the data from all the different robots all put together. And the robots are quite different from one another. They include everything from small-scale RC cars to full-scale ATVs. So this is a fairly complex setting that requires very broad generalization. With this training, we can actually get a model that can not only control all of the robots in training, but can actually generalize in zero shot to entirely new robotic platforms. For example, it can fly a drone. Now, the drone is pretending to be a car in the sense that it's flying at a fixed altitude, but the model has never been trained on drones before, and in zero shot it can fly through hallways. We've recently scaled up the GNM to create VINT, the Visual Navigation Transformer, which is a much larger version of the GNM that uses transformer models and over 100 hours of training data. This model can also generalize in zero shot to new settings. For example, it can generalize in zero shot to control a quadruped robot to walk around, in this case on a university campus environment. Now, the model is not controlling the legs, it's still using the manufacturer control to actually move the legs, and is just deciding the global direction, but it's doing vision-based navigation for this very different robotic platform. The other exciting thing we can do with VINT is actually apply methods similar to prompt tuning to extend it to other settings that are not just goal conditioned. For example, we can freeze the entire VINT backbone and retrain the encoder so that instead of encoding goal images to specify the task, we can encode other task specifications like GPS coordinates or even turn-by-turn instructions like turn left or turn right. Based on this, we can fine-tune VINT from a small amount of data to drive a simulated autonomous vehicle in Carla. Here, VINT is pre-trained on real data from many different robots and then fine-tuned to Carla, where it can take turn-by-turn instructions like turn left or go straight. So here we can successfully prompt tune our way to go from image goals to routing commands. So VINT is a very flexible model. It can be used to solve a variety of tasks. We have a variety of other tasks in the paper, including exploration, mapping new environments, and controlling other types of robots that were not seen in training. The other thing we can do with multi-robot pre-training is pre-train for downstream RL. So here we train with offline RL, in this case with an algorithm called IQL, on the GNM training set, and then we perform online reinforcement learning to learn to race around a building with a method called RLPD, which is a sample-efficient online RL technique. Now, in the beginning, the policy doesn't drive very well. It still collides with things, but it roughly starts making its way around the building. But 10 minutes into training, it could actually successfully navigate the building. 15 minutes in, it can make its way around the hallways, occasionally hitting the walls, but mostly making its way around. And then 20 minutes into training, or 25 minutes into training, it can drive around the hallway quite quickly. In fact, by this point, the speed of the vehicle actually matches the best time that the expert human driver, the first author on the paper actually, was able to get using the same first-person camera. Here's the first-person camera. If you use a third-person view, if you basically follow the robot, you can drive a little bit faster, but from the first-person camera, the learned policy is actually about the same. And I think that's actually pretty remarkable because this policy is learning to drive this vehicle entirely from pixels. Now, some of you probably know that learning to drive from pixels typically takes an inordinate number of samples. The fact that you can do it in just 25 minutes with these offline RL initializations, I think is actually very promising for future use of these techniques. We can also do this outdoors. So here is the initialization 5 minutes into training. It's not very good, it still bumps into things, but it starts making its way around the building. But after 20 minutes of training, it can actually make this lap around this building, and it shows some interesting emergent behavior. So you can see that on the bumpy grass, it's pretty hard to drive. So the checkpoints are actually on the grass, but in between those checkpoints, it actually has this bias to try to follow the paved trail so it can go a little faster. So here it has hit the checkpoint, but after hitting the checkpoint, it tries to prefer to be on this paved path. And here's the first-person view. So I think this really illustrates the idea that I motivated with in the beginning of the talk, where you can do offline RL pre-training on a variety of different data sets, in this case for many different robots, and then perform very rapid online training to adapt to a particular domain, much like we might want our space exploration robot to adapt to whatever exploration scenario it might find itself in. So for the last topic I'm going to discuss, I'll bring this back around, and instead of talking about how data-driven AI can help us with decision-making problems like robotics, I'll bring it back and talk about how RL can actually help with generative models. So if you recall in the beginning, I talked about how data-driven AI is all about using data. Reinforcement learning is all about optimization. So far we've talked about how to make RL and control better by leveraging data, but can we make generative models better by leveraging RL? Now, why should we worry about this? Well, the pictures that we saw before, they're impressive because it looks like something that a person might draw. The problem is that we don't just want to make pictures that already exist. A big value of these generative models is that they can solve new problems. We don't necessarily need the same picture of a painting that another painter already painted. We might want something unusual, like a dolphin riding a bicycle. So if we put a dolphin riding a bicycle into Stable Diffusion 1.4, this is the picture we get. Now, of course, maybe newer versions of these diffusion models will do better, but this is what we get out of 1.4, so let's work on that. Why do we get this picture, first of all? Well, this is a little bit like an artist's Move 37, in the sense that a dolphin riding a bicycle requires emergent behavior. It requires a novel solution to a new problem. There are pictures on the web of dolphins riding bicycles because dolphins can't ride bicycles. So we need something new. We need optimization to get emergent behavior. Now, how do we optimize for a picture that is a good picture for a dolphin riding a bicycle? There is something actually well defined about this, because we could say that, well, a good picture of a dolphin riding a bicycle is one where if someone looks at that picture, they'll say this is a picture of a dolphin riding a bicycle. So that's what we're going to do. Now, in lieu of actually showing these pictures to humans and asking them to describe them, we'll actually show them to another AI model. So the way that our system will work is we'll generate a variety of prompts. The prompts are actually generated procedurally from a grammar. So in this case, it'll be animals performing different activities, like a monkey washing dishes, a raccoon riding a bicycle, a snail playing chess, and so on. These will go into a diffusion model, starting with Stable Diffusion 1.4. It'll produce a picture, and then a vision language model, Lava, will be asked, what is happening in this image? And it will produce a caption. So the vision language model basically provides a reward based on semantic content. And then this caption will go into BERT to get BERT score, comparing the caption and the original prompt. And the diffusion model will get a reward based on the similarity between the description that lava produced and the prompt that was given to the diffusion model. Now, this is a fairly difficult task because if you take the picture on the left, imagine that a person had no context about what the diffusion model is trying to produce. You just saw that picture. What would you say? Well, you might say maybe it's a monkey with some bowls, or you might say that the monkey is eating something, right? It's not at all clear what's supposed to be going on. So this is a fairly difficult reinforcement learning task. It's also not completely obvious where the benefit comes from because in some sense, there is no additional knowledge being put in. It's just what this lava model learned from data. But remember that the diffusion model is just trying to match the distribution in the data set. It's not trying to optimize for a particular outcome. In fact, if the prompt, a monkey washing dishes, is extremely unlikely, the model would actually prefer to produce an image that is more likely to occur on the internet as opposed to one that more closely matches the prompt. So by running RL, we're teaching the model to solve the task rather than merely copying the data. And that is a really big difference because once you put optimization into the mix, now we have an engine to enable that emergent behavior, the engine to enable things like Move37. Now there's a technical challenge with this, which is that diffusion models are not easy to optimize with RL. The reason is that diffusion models don't actually provide easy log likelihoods. If we want to use something like likelihood ratio policy gradients, we typically need to compute quantities like the gradient of the log probability of some image with respect to our model. We don't have this in closed form from a diffusion model. What we have is the log probabilities of each diffusion step, meaning each denoising step, but that doesn't by itself give us the log probability of the entire image. So we developed a new algorithm called DDPO, Denoising Diffusion Policy Optimization, which is based on a very simple idea. It simply treats every diffusion step as an MDP time step. And because we have closed form log probabilities for every step, now we can actually optimize the entire diffusion model with RL, treating it as a sequential problem where each step in the sequence is one denoising step. So this is the form of the basic policy gradient estimator, where the reward is the reward of the final image, and it's multiplied by the gradients of the log probabilities of each diffusion step for whatever context the time step is passed in. And this actually works really well compared to alternative approaches like filtering the data, cloning the best part of the data, reward-weighted regression. These DDPO methods are extremely effective at optimizing a variety of objectives like compressibility, aesthetic quality, etc. The importance sampling version, which is perhaps most similar to PPO, works even better. So this is a very effective way to actually optimize diffusion models with RL. And I should mention that there's some concurrent work by Fon et al. That proposes a similar algorithm, although not in the context of using vision language models for reward supervision. Okay, but let's see what this does. Let's start with this dolphin riding a bike example. This is what Stable Diffusion 1.4 produces. Now we pass this to lava, we ask lava to caption it, and then we use that with RL. Now I will say that here I'm going to show the evolution of this dolphin image, but the optimization is actually optimizing for a distribution of prompts. So this is not a model that's just optimized for this image, it's actually optimized for a distribution of animals performing activities. So after some optimization on a variety of prompts and images, these are the images we get. Now this image is better because you can see that there's a dolphin and there's a bicycle, but the dolphin is not actually riding the bicycle. So after a few more steps, now we get an image like this. Now we see some creature riding a bicycle. The creature doesn't maybe look very much like a dolphin, so perhaps lava might not caption this as a dolphin riding a bicycle, it might caption it as something else. After a few more optimizations, the animal starts to look more like a dolphin, and at the end it's very clearly a picture of a dolphin riding a bicycle. I think if you saw the picture on the right, that's probably what you would say. And I should say, by the way, that the way that we're producing these visualizations is we actually pass the same random seed multiple times over the course of optimization. That actually gets us these pretty consistent images. Here are some more examples for different animals. And here are some plots that show the evolution of BERT score over the course of training. One of the things that I want to draw your attention to here, so the thin lines in the background show the individual animals and the color denotes the activity. Some of them start out very low and improve significantly. Some of them start out higher. The dolphin is probably the worst example in the sense that it starts off with the worst possible image, which means that in the beginning, the dolphin example by itself really doesn't have much gradient signal. So most of the gradient signal for the dolphin actually comes from the other animals that are a little bit closer and that kind of pull up everything else. I think these are really interesting images to look at, not just because of the amount of improvement that we see going from left to right with RL, but also because we can see some interesting patterns emerge. Like, for instance, the images on the left at the beginning of training tend to look more like photographs. The images on the right more consistently look like illustrations in children's books. Perhaps it's because animals performing activities are more likely to be in children's books and illustrations rather than in photorealistic pictures. But you can see in many cases very large improvement in terms of the quality. For instance, the bear washing dishes in the second row on the left starts off from a picture where there's seemingly a toy bear on a sink to one where there's very clearly a bear that is actually washing the dishes. After training this model with RL, we can also give it new prompts that were not part of training to see if it generalized. Now, this is a very non-trivial experiment because the model was not actually trained with RL to optimize these particular prompts. It was trained with RL to optimize other prompts, so if it performs better for these prompts, it's because it learned something general about the combination of animals or creatures in general performing activities. Even for something as esoteric as a robot fishing in a lake in the lower left corner, you can see that after RL optimization, the image is significantly more semantically meaningful. All right, so to wrap up, I talked about what we can accomplish if we combine data and optimization. I talked about the foundation of offline RL algorithms that can make this possible. I talked about how applying these offline RL methods to broad robotics datasets can enable robots to perform a wide range of different tasks and actually fine-tune very rapidly to new behaviors. I talked about how we can scale this up with multi-robot training, where training multiple robots in this way can enable new robots to perform navigational tasks and provide a solid initialization for online RL fine-tuning with new robotic platforms. And finally, I talked about how these ideas are not just useful for robotics, that we can take the same optimization principles and apply them back to generative models to get generative models that are more goal-directed, that are more aimed at solving actual problems that users want them to solve, rather than merely copying internet data distributions. To add a little bit of philosophy to this, I think that there is something very deep about the notion of combining optimization and data-driven learning that was also articulated very nicely in an essay by Richard Sutton called The Bitter Lesson. Now, a lot of folks are familiar with this essay, but I suspect that not as many people have actually realized that the lesson is about two things, not one. So many people take this lesson to mean that we should use data, but it says a little more than that. So roughly speaking, this quote, I think, summarizes the main idea. We have to learn the bitter lesson that building in how we think does not work in the long run. The two methods that seem to scale arbitrarily are learning and search. A lot of people take this to mean that the core to effective machine learning is to basically take lots of data and shove it into lots of GPUs. And that is actually part of the bitter lesson. But notice that the bitter lesson is about learning and search. Clearly, learning works very well. But what is this bit about search? Well, learning is using data to extract patterns. So that's the use of data, and I talked about that extensively. Search is the use of computation to extract inferences. Learning is about data, search is about optimization. And really, we do need both of those things. Learning is very effective to extract the patterns in the data, but ultimately, successful machine learning is not just about extracting patterns, it's about leveraging those patterns to solve problems. And that's where the search comes in, some optimization process that uses typically iterative computation to make rational decisions. Learning allows us to understand the world, search leverages that understanding for emergent behavior. Data without optimization doesn't allow us to solve new problems in new ways. Optimization without data is hard to apply to the real world outside of simulators. Hopefully the topics I discussed provide you with some convincing evidence that this might be the case and some directions that we could go in the future to study these things. But I want to end with a bit more philosophy about some of the bigger picture of where this might take us. And to talk about that bigger picture, we can ask a fairly big question. Why do we need machine learning? From that question, we can step back and ask an even bigger question. Why do we need brains? There's a somewhat reductionist but very interesting answer that was provided by Daniel Wolpert, who's a neuroscientist that studies brains. Wolpert said that we have a brain for one reason and one reason only, and that's to produce adaptable and complex movements. Movement is the only way we have of affecting the world around us, and to understand movement is to understand the whole brain. And I think there's a lot of truth to this, that in the end, for a system that makes decisions like the brain, its value is in its outputs. So a postulate I might propose along the same lines is that we need machine learning for one reason and one reason only, and that's to produce adaptable and complex decisions. This is not a trivial statement. It means that really the value of a machine learning system is in the decisions it produces, not in the patterns that it recognizes. And that's very obvious, of course, in robotics or in autonomous driving, but even for a computer vision system, the decision might be the consequence of the label that it chooses. Tagging a user in a photo, detecting an endangered animal in a camera trap, these are decisions that lead to consequences. A system that makes the right decisions might be more valuable for its users, just like those generative models might be more valuable if they produce images that actually match up with the semantics of the prompt. What this implies to me is that we should really be thinking of machine learning problems fundamentally as decision-making problems. And that means that if we want to pre-train large foundation models, we should be pre-training them in ways that reflect the capacity to make decisions. Perhaps we can take large amounts of data from a variety of different tasks, including data from the web, including videos, including data from robots, perform some kind of large offline RL pre-training process using either goal-conditioned BC or goal-conditioned RL or self-supervised skill discovery, and then use this as a foundation for downstream decision-making tasks. And insofar as we need machine learning to make adaptable and complex decisions, this kind of more decision-centric pre-training might lead to significantly more powerful pre-trained models, better large language models, better generative models, better computer vision systems that are more suited for applications where the decisions really matter. So I'll leave you off with that thought, that perhaps combining data-driven learning and controller optimization will help us build more powerful self-supervised pre-training methods in the future. I'd like to thank my students and colleagues that carried out much of this research that I described, and I'd like to thank you for listening.